Hello everyone and welcome to our lecture on phasors and vector review. I'm going to go ahead and work out a few examples based on the handout that you were assigned. I'm not going to work out every single example, but from what I give you, you'll actually be able to go through this handout. And then probably review a little bit about trigonometry. So let's go ahead and start off with the very top, the objective of this handout. The proper manipulation and representation of vectors is paramount for AC circuits, and this is what we're going to be covering the rest of this semester. Addition, subtraction, multiplication, and division of vectors in both rectangular and polar forms are examined in both algebraic and graphical forms. Representation of waveforms using both phasors and time domain graphs are also examined. So we're going to go ahead and just do this a couple of these problems so you can get an idea of how to do these. And number one is perform the following operations, including phasor diagrams where appropriate. And so basically this is arithmetic of complex and polar notation, where we have two numbers that we're going to either be adding, subtracting, multiplying, or dividing. And we're going to see that one set of notation is actually easier for on one type of operation. For example, the complex numbers. Let's go to start off with this very first one, and hopefully my writing is legible. So problem number one. This is going to be kind of easy. Let me get a pencil first. We have, I'm writing kind of slow because I'm trying to write very neat. 6 plus J10 is our first problem, and that's all in parentheses. Plus, now remember I told you this is actually a lot simpler than you realize. And I know you've covered this in the past, but again, this is just review. Plus J2. And basically, just like you do in algebra, it's add likes, and so like with like. In other words, we have a constant here, 6 with 8. And we know that we can actually add those together, and then we have our j components. So we add our j components together. So you can actually just do this. Let me write this down here to make this a little more visible. 8 minus j2, and we're adding this. So just like we would regular arithmetic, where we end up with 14 plus j8. And if I did my arithmetic correctly, that should be the answer. So let's go ahead and go to a different problem. What if we were given something in polar notation? So you can see when we're adding in complex numbers, and it's actually pretty straightforward, very easy. But when we want to add something and we have polar notation, let's go ahead and jump down to problem number 3, where we're given an amplitude. In this case, we'll just say it's a magnitude word. I got to pick the pencil again. It's 10. I'm on problem number 3 now, at an angle of 0, plus 20 at an angle of 90. I'm not going to work this out. I'm going to let you plug in the numbers. Let me see if I can actually write this small enough. So we want to actually, in order to do this, we actually have to write this in the complex number format, which is Z is equal to A plus B or JB. We do this in engineering. Mathematics, they'll tend to use the script I. But the I, if you remember, can be is used for other things. So we use J here in engineering. And if we look at a Cartesian coordinate, mine is not that straight. Let me pick a different color. But we have some vector at some angle. We have the A and B, we'll call them the legs of the vector, where R is a resultant here. So from that, we can actually go ahead and solve for or at least derive the formula for finding out what these components are, the x component and the y component, or in this case, the a component and the b component, if we make this the j vector and this the a vector. So I'm going to write this in a different color, that way we can keep track of our progress. And I'll try to write as small as possible. So let's go ahead and start off with the Pythagorean Theorem, where we have r squared is equal to a squared plus b squared. And so we can use this, and we'll use it a little later down the road to actually find the components. But we can also use some trig identities. So we know that if we're looking for cosine theta here, again, without knowing any of the actual values, we can write something like this. This should be familiar from, I know some of you may have not taken trig yet, but are currently taking pre-cal. But you should be learning something that looks like this, where you have cosine of a over, and in this case, it should be r. And that's the formula that actually includes the a component of this vector. And if we're looking for b, and I'm trying to write this slow and neat, sine theta, and hopefully this should be review for some of you, or it should start getting your brain to remember. Oops, sorry. I don't know why I wrote 2. It should be r. Right. If we're looking at the value of the b component. Now with just a little bit of algebraic manipulation, we can just multiply both sides by r to give us r cosine. Again, I'm sorry about my writing. R cosine theta to equal a, and r sine theta. Actually, I'm getting a little better at this. Is equal to b. And so, using these formulas, r sine theta and r cosine theta, we can actually find the legs of a and b for this complex notation. Now, we kind of have to do all of this so that we can just do this basic addition of 10 at some angle plus 20 at some angle. So let me see if I can keep writing and include all this without having to erase all of this and start on a new sheet. So let's go ahead and go back and substitute into that original formula, z is equal to a plus jb. And by doing that, we get z is equal to, and we just go ahead and substitute our values for a and b here. We have r cosine theta plus, don't forget j, r sine theta. Okay. And by doing this, we can actually convert our polar notation into our complex notation. And once we do that, we can simply add likes and like to like. And just to give you an example of what the whole thing should look like, we're going to do 10 to the angle 0, and that would look something like, and I'll try to write just a little bit smaller, 10 cosine theta. Okay, and we actually haven't found theta yet. We're going to have to use tangent for that. Plus j 10 sine. I'm sorry, we do have the angle. It's actually 0. Sine 0. That should be a 0. And so this should be a 0 right there. And then we're going to do the 20 at angle 90. So we're going to do plus 20 cosine 90 plus, don't forget the j, 20
sine 90. And again, I'm not going to work this out for you. Let me just put the z right here. Is equal to. So if you calculate the numerical values of all these and add likes to likes, in other words, 10 cosine 0 plus 20 cosine 90, and j components 10 sine 0 plus 20 sine 90, you should get this complex number of z equals a to b, and that should be your answer. And you do the same thing for whether you're adding or subtracting polar notation. Okay. So let's go ahead and move to multiplication. Now, what I'm going to do is, there's a certain way you can do polar notation, just like you do in algebra. So what we have, let's go ahead and jump down to problem number, I'm going to show you an easy way of doing this. I'm going to start with 8 through 12, and then we'll go ahead and jump back through 6 through 7, because I think you know how to do conversions now from complex numbers to polar notation and polar notation to complex numbers. You should be able to go back and forth right now. But number 6 and 7, they throw these complex numbers where you're multiplying them and dividing them. Now you can go ahead and use the FOIL method and actually multiply those numbers out, and it gets kind of muddy. But I'm going to show you another way of doing it, how easy it is if you go ahead and convert them to polar notation first, and you can actually add and multiply and divide polar numbers easier. Just the way we do with complex numbers, adding and subtracting is very easy. Polar notation makes multiplication and division very easy. So let's go ahead and jump to problem 8. So problem 8 is 10 at an angle of 0. And that one we are multiplying 10 at an angle of 90. I'm going to show you how easy this is. So what you do when you're multiplying polar numbers, you basically multiply the constants out here to get the magnitude for your result, and 10 times 10 is just 100. And the angle is the addition of the degrees here. So we're adding up a little plus right here. Plus that. Give me the final result of my angle. And so 0 plus 90 is going to give us the result of 90 degrees. And so the final answer, I'll write over here just a little bit clearer, is 100 magnitude at 90 degrees. That easy. Now remember, if it's a negative angle, you're adding a negative number, and it's just like adding and subtracting there. And so that's why it's easier to do addition. I mean, it might be easier to convert a rectangular Cartesian type coordinate to polar notation if you're going to be doing multiplying and dividing. Now let me show you how easy it is to do division as well. So let's go ahead and look at number 10. Problem 10 is a magnitude of 10 at an angle of B. And we're dividing, well, I'll put a division sign here, but I'll write it in a different way. So we're dividing that by 5, a magnitude of 5 at an angle of 10. And so let's go ahead and write this in the way that we normally write long division. 10 at an angle of 90, sort of in the fraction mode. 5 at an angle of 10, getting a little better at writing. And basically, again, with the magnitudes, we do the division operation. So 10 divided by 5 is going to give us 2. That's supposed to be a 2, not a z. Right. And when we do the angle, when we're doing division, now we actually subtract. As we're multiplying, we are adding the, let me give you my little hand, there you go. So multiplication, where we're adding those angles. In division, we're subtracting the bottom angle from the top. So this would actually give us 90 minus 10, And I'll write it out here so you can, it might actually help you. Minus 10. This gives me a second opportunity to write a better 2. There you go. At an angle of 80 degrees. And there you go. Arithmetic for complex numbers and polar notation. So when you go back to 6 and 7, where you're multiplying and dividing complex numbers, you're going to have to convert those to polar notation, and you can do that now with the sine and cosine function. And then you can do addition and subtraction very easily. Okay. Now, let's move on to the next part. Draw the following expressions as time domain graphs. So we had a question in class about radians versus degrees. And we talked about the notation for radians actually being equivalent to pi. Right? Or not equivalent to pi, but including pi. So what I'm going to do right now is just kind of give you a quick formula to convert degrees to radians, and then radians to degrees. Right? And I don't have my pencil. There we go. I think I'll do a happy color. We'll do green. Right? And so if you want to convert from degrees to radians, and I know the problems here are asking us to convert from radians to degrees, except for one problem. They're giving us the answer in radians. In the problem, they're given radians and degrees, and you're going to have to convert to 1. So let me show you how this looks. So if I want to convert, and also there goes my I almost wrote a 0. So if I got something in degrees, and I want to convert that to radians, I have to multiply by, and we're not going to, you'll learn this in your Cal and your Trig class, we're not going to derive y. It's pi divided by 180. And I can actually draw the unit circle so you can kind of get a better understanding of this. And this will actually give us the degrees in radians. So this degree is not the same as, okay, let me just, you can't see what I'm doing. This degree is not the same as this degree. Right? This is going to be something in, 0, 45 degrees, 90 degrees, 100 degrees. This would be something that includes pi. So let's look at number 13, for example. So number 13, we're given a voltage. Oh man, that's a bad B. Which is equal to, it has an amplitude of 10. And since this is alternating current, it's going to be at a sine wave of 2 pi times 100 t. And it's asking us, draw the following expression as time domain graphs. And so if you see something with pi in it, right, I'm going to do this. You need to convert that into a degree, right? So what we end up doing is you have to convert this from radians, since you know it has pi in it, it has radians. Plug that number in here and convert it to degrees. So if you want to do that, remember we work backwards. I'll put, let's see, do like this. We'll say this is in radians. I'll put a little subscript r here. And this divided by pi times 180 will equal our degrees. And I'll put just a D there for degrees. And in order to understand this a little further, let me go ahead and draw two graphs, and we're going to have to go to another white screen. Oh, I didn't even do that. I wanted to draw a graph. So just to make sure you all know what sine and cosine is. And I'll do the best I can with what we got here. So this first one's going to be cosine. I'm going to do cosine in red. Just put cosine. I'm sorry. Let's do sine. Sine in red, because sine starts at the origin. Sine is in red. And so if you look at a sine wave, and we'll do this actually in the lab, if we had a function, in this case it's v, but you'll see it written in mathematical books such as, I'll do it over here, y, the amplitude y is equal to sine x that sine actually starts off at the origin. So sine 0 at 0 degrees is 0, and it actually moves like this. I'm actually doing really, really well. Oh yeah. Well, kind of okay. And I'll do cosine at a different angle. And then we're going to convert this to the unit circle so you can kind of understand, get a little mathematical review on why this is. Let me pick a color that's slightly different than red. We will do blue. And let's do y is equal to cosine x. Now we know that y at cosine of 0 is actually 1. And let's say this is a unit of 1 right here. So remember, we have no coefficient right here. And same thing with here, we have no coefficient. So the highest this can be is 1, unless we had some magnitude like 10 or 15, and then it would be that magnitude. So let's go ahead and do this here as 1. And so when we start off at x being 0, cosine actually starts off at its maximum amplitude. Now let me see if I can draw this. This is the way cosine would go. Cosine would actually be at a different phase from sine. So when this is high, sine is 0, and when sine is high, cosine is 0. So let me do my points first. I think this will help me. When this is high, when this is low, this should go like this. And okay, so when this is 0, this is high in the negative 1. Let me do this real quick. I'm going to draw another. Oops. There we go. Okay, I'm going to do it right there. Okay. And we're going to call this our negative maximum amplitude right there of negative 1. Or some negative max. And put, let's go back to blue. Okay, now I'm a little bit, I got my bearings here. And so when sine is 0, and it's going in the negative direction, cosine will be at its highest negative amplitude, which should be right there. And then our next point would be like this. And so you guys get the idea. There's our sine wave in blue, and there's our sine wave in red and our cosine wave in blue. And if we were to continue this, it would actually just continue going on, where one would be following the other. So we say that one is actually leading the other, and one is actually lagging behind the other. This is where we get lead and lag. So For example, right here where cosine, you can't see where I'm pointing, blue. Cosine right here is 0, and sine is at its max. Remember, sine is leading. It's starting off at the high, and it's going down. And then, cosine is leading, starting up at high, and then it's already starting into its waveform, as where sine is starting and it's following, right? So as cosine is already going down to the negative amplitude, so is sine. Sine is actually following and going down to the negative amplitude. And we say that these are actually leading and lagging each other by 45 degrees. You can't see it right here. If it was actually leading, yeah, you can't see it right. It's kind of hard to see. It's supposed to be going right down the middle here. Okay, so by that is what we mean by drawing the following expressions as time domain graphs. So now, when we're looking at a like number 13, let's go back to number 13. I'll see if I can actually draw it right over here in the slide. And we're looking at all sine functions. So all of these sine functions are going to start off at 0, except for the one that has plus 45. Right? So number 13 says b is equal to 10 sine 2 pi 100t. Right. And so we know that the magnitude is going to be 10. So when we do our magnitude, and I'll draw this in a different color, I'll say orange, and I'll draw an orange line here. So this is going to be this one. And so instead of 1, it's going to be 2, 3, 4, 5, 6, 7, 8, 9, 10, way up there. Same thing down here. 1, 2, 3. I know this is not equidistant, but just so you get the idea. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and way down here. So we're going to actually have a sine wave that starts at 0 and follows this pattern right here. Now the next part, the 2 pi 100t, that's going to tell us the frequency at which it cycles. So how many times per second will this thing cycle? So if we were to plug in a time unit of 1 second, how many times does this actually cycle? We can kind of do it without even converting this to degrees. So for every pi, we know that it goes 180 degrees. And let me show you what this means now. Hopefully I haven't lost any of you. So we've got, if I do that, nope. Start somewhere over here, maybe right there. If I draw a circle, I can't actually move it, so I've got to be real careful where I draw my circle. Okay, that's good enough. And we draw some. That is not what I wanted. I have to draw a line. This is not going to look as pretty as I had hoped. And I'll redraw this middle line right here. Forget this squiggly line that I have down there. So we start off at 0. Oops. If we start off at 0, excuse me. That's equivalent to, gosh, that doesn't look like a good 0. You get the idea. That's equivalent to 0 degrees. So 0 pi is equal to 0 degrees. But if we were to go up here to 90 degrees, 90 degrees, if we were going to that formula that we did in the previous slide, it would be equivalent to, let me just write 90. Not really good, is it? Pi over 2. And go ahead and plug these numbers in if you need to do the calculations. again, so then if we go to 180 degrees, now we can tell degrees easily because we're used to using degrees. 180 degrees just being completely to the side. This would actually be equal to pi. And then if we were to go to 270 degrees, and so this might look familiar to some of you from who took calculus or are going to take pre-cal right now. This is equivalent to 3 halves pi. And guess what? When we get back all the way to 0, or 360 degrees, and without making this look too confusing, I'll do it in a different color. 360 degrees, which is equivalent to 2 pi. So that means that 2 pi is actually equal to 1 full revolution. So if we go back to this problem here, and we didn't have this 100, and so for every 1 second, we would have 1 revolution of the sine wave at an amplitude of 10. And that would be pretty simple. So this would be, we go up, and let me show you the mouse on that so you can't see what I'm saying. So we started right here, look at this red sine wave. So if we started right here, we would go up, we would go down, and we will come back all the way up to 360 or 2 pi in 1 second at an amplitude of 10 if we didn't have the 100 in front of that t. But now what we're saying is we're going to have not just 1 full revolution, we're going to have 100 revolutions of this within 1 second. So in this case, I think I can go and erase this or I will actually try to draw it and superimpose it over this so you can get an idea. So we want to draw 10 sine 2t 100 at 100. It will look like 100 sine waves, full complete sine waves, before it gets to 2 pi, and 2 pi is right here. Right. And we'll just make that right there. But since we're doing time domain, right, this is 1 second. 1 second to complete 2 pi revolutions, right, which is 1 whole revolution. But again, we have 100, and so your graph, your drawing, or your sketch, however you want to call this, is going to have 100, and I'm not going to expect you to count all 100. At an amplitude of 10, what you can do is do something like, not this bad of a drawing, please. But you get the idea. We have 100 cycles. Yeah. Guys, also have to remember my hand is still sore from the accident. Of course, there's no way I'm going to get 100 before I get to that full revolution with this, schematic. But you get the idea. There's 100 of these cycles, and of course I'm not, it's all crooked, but this is 1, 2, 3, 4, 5, or do 6, but in reality we have 100 cycles, and it would really look more like, real close like that. And so if you can just put as many as you can and say there's 100 peaks, 100 full wave cycles here, so I know that you know what that means, go ahead and draw it that way. Or if you want to run it on some software that you know of and print that and upload that as your homework, you can do that as well. If you know any web-based software that'll do this, send me an email and we'll use this to draw the graphs. Now, there is an issue that I see with one of them. Let's go ahead and erase this. The second one, I think they meant to put let me draw that out for you to get an idea, which is number 14. V is equal to 20 sine 2 pi, in this case is 1000 t, plus 45 degrees. Right, and so in this case we have degrees and radians in the same block. I think they meant to do this because you can't add, if radians was outside this, you wouldn't be adding anything. In other words, if it was 2 pi 1000 t, sine of that times 20 and adding 45 degrees to all of that, that actually would not make sense. because 45 degrees, you couldn't add it to this magnitude. They're two different things. So that degrees, they should have meant to put inclusions here and there, so it will be sine 2 pi t 1000 t plus 45 degrees. I know one's in radians and one's in degrees, but at least they're both a measure of the same thing. We can convert back and forth. So you can convert 45 into pi and graph this. So what this would be saying is, wherever you're starting off, that you're going to be starting off at plus 45 degrees. So again, just to give you a quick idea, what would it look like when, let's say, t was 0? Are you actually starting off at 0? Or are you actually now starting off at 45 degrees? So this thing would actually be shifted somewhere along the x-axis, just the way we did in algebra. So this number shifts this 45 degrees. And so basically what we're doing is turning this into a cosine function. And then number 16 through 19, these are just word expressions of the same concepts we did now. And I think from this, you can do the rest of the homework. So go ahead and complete this, and we will actually go over these in class. I want to see what you can do. Thank you very much.